Okay, welcome to lesson 44. This is just the first part of lesson 44. I'm going to post another video on the other one, but I wanted to get this one up before tomorrow's test. Okay, we've been doing chain rule, but we haven't been calling it chain rule. All right, we've been using what we think of as Newton's notation. So if function h of x is a composite function, f of g of x, then what we've been doing is that we've been saying the derivative of h is f prime of g of x times g of x times g prime of x. So the derivative of the function times the derivative of what's inside. Now you don't know you've been doing that. Okay, you've been doing problems. Here's an example. Let's just do something simple. We're going to let's let y equal cosine of x cubed. Okay, y equals cosine of x cubed. All right, the way we've been doing this is we're going to let y equal u cubed and u equals cosine x. All right, so to find this, we say that dy is equal to 3u squared du. But what's du? Du, derivative of the cosine, is negative sine x dx, and then we've been substituting in. So that dy equals 3 times, what's u? U is cosine x, squared, times du, which is negative, and put it out front, negative sine x dx, but instead of putting the dx over here, we just divide both sides by it, and we say that that's dy dx. Now look at this. What you did was you took the derivative of this function. What's the derivative of y equals something cubed? All right, let me change colors. All right, the derivative of that is 3 times whatever is in there squared, right? That's the derivative of y, so that's f prime of g of x times the derivative of what's inside. What's the derivative of cosine x? Negative sine x. So what was inside? Cosine x. All right, so we would get the same answer if we think of it in Newton's notation. Take the derivative of the function, right, but leave that function inside there, then multiply it by the derivative of what's inside. We've been doing this longhand, and I kept thinking some of you were seeing the shortcuts. That's why I kept turning you off. Nope, don't shortcut, no shortcut yet. But this is a shortcut where you just recognize it's the derivative of this, so 3 times that squared, times the derivative of what's inside. Well, what's the derivative of what's inside? Negative sine x. All right, so that's the way Newton works it out. H of x is a composite function, f of g of x, so h prime is f prime of that function times the derivative of what's inside. Now Newton's notation can get a little hairy when your function is a function inside a function inside a function inside a function inside a function. Then it gets kind of just keeps going on and on and on, and that's why they call this the chain rule. You feel like you're stuck on this chain. So sometimes it's easier to use the Leibniz notation. So let's get rid of Newton here and let's look at the Leibniz notation. If I can find it, there it is. Okay, Leibniz. All right, the way Leibniz works this out is he says dy dx equals dy divided by du times du divided by dx. So see, we just multiply those through, dy over du times du over dx. So let's look back at that same example. Cosine of x cubed. So that's y. All right, so same thing. I'm going to let y equal u cubed and u equal cosine x. So what's dy du? dy du is just 3u squared. And what's du dx? Du dx is negative sine x. So what happens when I multiply dy du times du dx? I end up with dy dx. So dy dx is just these two multiplied together. 3 times whatever u is squared times negative sine x. Well, what was u? Cosine x. Now that looks familiar, or at least it should look familiar. So this is just a different way to do the exact same thing we've been doing. This is why it's called chain rule. It goes on and on and on and on. So dy du times du dx will give you dy dx. Okay, so let's look at an example problem. Let's look at example 44.1. Okay, using Leibniz notation of y equals u squared plus 4u and u equals 5x cubed, we're asked to find dy dx. Okay, so let's look at the first one. What was the derivative of y with respect to u? Dy du is simply going to be 2u plus 4. Well, what's du dx? Du dx is 15x squared. Right? 3 times 5, drop it down 1, 15x squared. So get dy dx, I just take dy du times du dx, du's cancel, and I'm left with dy dx. So dy dx is equal to, what's dy du? 2 times whatever u is, plus 4 times 15x squared. What was u? U was 5x cubed. There it is, 5x cubed. So simplify that out and I would get 2 times 5, 10x cubed plus 4 times 15x squared. Alright, so this would be using Leibniz notation. And apparently the textbook continues to multiply that. 15 times 10 is 150 x to the 5th plus 15 times 4, 60 x squared. Right, so there's my final answer. Alright, and so that's an example of Leibniz notation. Let's look at another example using Leibniz notation. Alright, if y equals sine t and t equals 1 over the square root of x, then what is dy dx? So well, then it just tells me dy dx. Oops, why not? I always forget to do that. Okay, no, not that one. Go away. This one. There we go. Dy dx is equal to dy dt times dt dx. Now, why did I choose dy dt and dt dx? Because I look at my function. Y is a function of t and t is a function of x. So I can find how y changes as t changes. Remember, that's just the slope. What's the slope of the sine of t? So dy dt, derivative of the sine, is the cosine of t. And t, this is x to the negative 1/2. So dt dx is negative 1/2 t to the negative 3/2. So dy dt times dt dx is going to be negative 1/2 cosine of whatever t is. Well, let me start this again. It's going to be, see, dy dx is going to be, pen back, cosine t times negative 1/2, put the negative out front, negative 1/2 divided by the square root of t cubed, right? But t is 1 over the square root of x. This is getting more complicated. 1 over the square root of x. So this is going to be negative cosine times 1 over the square root of x, times 1/2 divided by the square root of 1 over the square root of x cubed. Now that's kind of messy. Let's see what it simplifies to. Cosine 1 over square root of x Okay, whoops, I found my mistake. My mistake's right here. dt dx is x to the negative 3/2, not t to the negative 3/2. So this becomes x to the negative 3/2. Oops, eraser. Pen. X to the 3/2, and I'm just going to erase all this and start over here. Okay, so let me back it up here a little bit. We've got cosine t, that's dy dt, cosine t, times dt dx would be negative 1/2 x to the negative 3/2. So I put that downstairs and made it the square root of x cubed. So we end up with just, turn my brush on, negative 1/2 cosine of t, t is 1 over square root of x, so cosine of 1 over the square root of x divided by x cubed is really x times the square root of x. I don't know if our textbook carried it out that way. X times square root of x. Oh shoot. Okay, your textbook doesn't pull this x out, but they should. So it's x cubed is the square root of x squared times x. The square root of x squared times the square root of x. That would be the square root of x cubed. So this should come out as just x. So I end up with negative 1/2 cosine 1 over the square root of x divided by x times the square root of x. Alright, so the real reason I wanted to get this up was to be able to give you a hint for extra credit. Alright, the extra credit hint. Hint for extra credit. Okay, right here, f of x equals sine x times cosine squared pi minus x. This looks like it should just be a simple product, right? 1 d2 plus 2 d1. So if I let 1 equal sine x, then d1 is going to be cosine x. That's not so bad. All right. The problem is 2. All right. 2 is a function squared, right? So something squared. So d2 is going to be 2 times that times derivative of what's inside. But what's inside has something inside. So let's look at, I just want to look at just the second half. How would you find the derivative of cosine squared pi minus x? And then you have to, that's just your d2, remember, because you have to do 1 d2 plus 2 d1. All right, but I just want to show you how to find d2. All right, what I'm going to let happen here is I'm going to do a chain rule 3 times. All right, I'm going to do chain rule 3 times. So I'm going to let y, if I turn on my pen, y equals u squared. Well, that's not so bad, right? Something squared. I know how to find dy du. So dy du would just be 2 times u. Ta-da! That one's easy. All right, but what is squared? Well, u is cosine of another function v. Okay? See that? What is squared is the cosine of some function. So the du dv, that's a v, du dv, derivative of the cosine is negative sine v, right? Negative sine v. But what's v? What's inside the cosine is, whoops, I don't need that parenthesis. What's inside that cosine is pi minus x. So now what is dv dx? It's just negative 1, right? The derivative of pi is 0, derivative of negative x is negative 1. So now to find dy dx, just this one, right? I'm just looking for the derivative of this one. Dy dx is going to be dy du times du dv times dv dx. You have to do this one 3 times, all right? So du's cancel, dv's cancel, leaving you with dy dx, which for this problem is what d2 is. So dy du is 2 times u times negative sine, now we're getting complicated, of v, whatever v is. Remember, I have to put u in there, and I have to put v in there, times negative 1. Well, there's my positive, so negative 1. So what is u? U is cosine of v, but what was v? Pi minus x. And the times the sine of pi minus x. All right, so the derivative of this whole thing right here, remember this is just d2 because you've got 1, 2. 1 d2. d2 is 2 cosine pi minus x, right? It's the derivative of this. It's something squared, so it's 2 times the cosine of pi minus x times the derivative of what's inside. What's the derivative inside that square? Its derivative of the cosine is negative sine of pi minus x times derivative of what's inside that pi minus x, which would be negative 1. That's what makes that negative sign go away. All right, so that's just a hint for one of the extra credit problems. I thought it would be a good practice for chain rule. Okay, I will publish probably 2 more videos on this lesson, one that I purchased and one that I'll put together for the alternative definition of the derivative.